Voilà, quelques mots avant de commencer. Je pense que je vous propose de commencer à l'heure. Christelle est dissipée. Donc bonjour à ceux qui sont là à distance. Donc je ne vais pas prendre la parole longtemps, mais je suis très heureux qu'on ait un cycle de séminaires de plus en plus construit, de plus en plus riche au sein du département, au sein du campus de Nantes. Et donc voilà, c'est toujours des événements stimulant. Je pense qu'on sortira tous de cette conférence avec beaucoup d'idées, avec beaucoup d'envie de faire de la bonne recherche. So now I skip to English. So I'm the deputy head of the campus here, and I'm very proud to be able to welcome you, Mr. Bolton, for your conference. I will say only a few words. I'm not a geotechnician. I'm the chief also of Christelle, but not a geotechnician. So I didn't know you by name, but I had an indication about the importance of your talk. I had on my screen the announcement of your talk last week, and a colleague of mine came in my office and said, "What? Malcolm Bolton is coming here and giving a talk." So I suspect this is a very important talk, and I think we are very privileged that you accepted to give this talk today. So thank you a lot in advance, and we are seeking forward to hearing you.
Ladies and gentlemen, friends and colleagues, it is my great pleasure to introduce our esteemed invited person today, Malcolm Bolton, who is a true pioneer in the field of soil mechanics. With a distinguished career spanning over 5 decades, Malcolm has left an incredible mark on the world of civil engineering and geotechnics. His academic journey began in Cambridge, where he graduated from in 1967, and where he developed a passion for civil engineering, which would later evolve into a lifelong fascination with the intricacies of soil mechanics, and thankfully for us, has led to all the work that he has done to date. Under the mentorship of the renowned Andrew Schofield, Malcolm was instrumental in setting up the UK's first geotechnical centrifuge in 1969 at Manchester University. He returned to Cambridge in 1980 as a lecturer, later becoming Professor of Soil Mechanics, Director of the Schofield Centre for Geotechnical Process and Construction Modelling, thankfully that name changed, and head of the Geotechnical and Environmental Group. He retired from the university in 2013. With over 250 publications to his credit, covering topics from pipelines to tunnels, foundations to embankments, and earthquake effects to landslide hazard reduction, Malcolm has made significant contributions to our understanding of the fundamental mechanics of granular materials. His work has not only influenced the field, but also earned him numerous awards from prestigious institutions such as the British Geotechnical Society in the UK, the UK Institution of Civil Engineer, the Institution of Structural Engineer, and the Canadian Geotechnical Society. Malcolm's impact extends across the world, as he was the founding chairman of the ISSMG Technical Committee of Geomechanics from Micro to Macro, which you might know as GM3, and the founding president of the International Pressing Association, IPA. His contributions have been recognized through several prestigious lectures, including the 52nd BGA Rankin Lecture in 2012, which I remember fondly. It was my first BGA Rankin Lecture, and the first ISSMG TC 104 Andrew Schofield lecture in Paris in 2013, which some of us here remember also fondly. Malcolm has personally always been a great source of inspiration and someone I thoroughly enjoy discussing research with. It is an honor to have Malcolm with us today, and I am confident that his talk will be a testament of his boundless enthusiasm and expertise in soil mechanics. So without further ado, Malcolm.
Well, thank you for that very kind introduction. It's a great pleasure to be back in Nantes, not only for the galette, but also for the good company here and being able to visit another premier geotechnical research facility, which this has always been. So by negotiation, the topic for my talk today, as you can see, is the strength and dilatancy of geomaterials. Some of you may know more about this than me. That is always the fate of a long retired professor, in which case you can teach me something in questions and answers at the end. What I'm going to talk about is perhaps novel only in that I'm going to merge together any understanding I have of the shear strength and friction, dilation, the data of the shearing of sands, clays, and rock joints, and the consistent finding that dilatancy, the tendency to expand on shearing, and shear strength of all these different geomaterials share much the same properties and behavior and respond well to the same graphs. I'm going to be talking about monotonic peak strength. So if during my talk it occurs to you to start thinking about cyclic load, for example, then you have gone beyond the topic of what I'm going to talk about. And I shall finish with a reference to the bearing capacity of sands. And there you may think of the gravity loading of a large, maybe circular base on the seabed for some offshore facility. And as you can see, the not so hidden agenda on the last line is to try and persuade the geotechnicians among you to dispense with the linear envelope of a Moore-Coulomb criterion. So we all know what these materials look like. So I've just shown a picture of a sand, a clay, courtesy of Pierre Delage, nice microscope views, and a rock joint from Nick Barton. I met Nick Barton about 20 years after I published Strength and Dilatancy of Sands. And we shared a coffee together. And we, at that point, realized that he had undertaken a study of the strength and dilatancy of rock joints, which effectively told an identical story, as you will see. It's the incompatibility in a granular material between an analytical macroscopic surface that you might want to analyze and the fact that grains or rock asperities collide with each other, that creates a confusion and a source of difficulty of understanding for geomechanics people. So you can see it best with, let me see what toys I've got. I've not got any toys. Okay, so the rock joint at the bottom indicates that I'm going to show you a very oversimplified picture of what's happening when you attempt to shear a surface in any of these materials. And the view that I have or had originally was bottom left, the interference between two micro scale protrusions. So you can think of the bottom picture there as a grain inside a simple shear or direct shear apparatus, interfering in shearing on the black plane with a grain in the lower part of the box. And at its most simple, the question then arises, will one of these grains break, permitting the shear to take place? Or will the top grain ride over the lower grain at what I've shown here is an angle psi, which, if it did do that, would be the angle of dilatancy. So in this very simplified view of friction and dilatancy, we have a macro plane of sliding, which is the black plane, horizontal plane in the diagram here. We have psi, the angle of the actual shear surface. If you had provided Coulomb with a microscope lens, he could have seen that the top block was not sliding on the black plane of sliding that he might have imagined. It's sliding on the red inclined plane. That is where friction is developed. So in addition to psi, angle of dilatancy, we also have phi mu, the inherent angle of friction, in this case of quartz on quartz, silicate on silicate. So in the very bottom line of the slide, the apparent angle that we call the angle of friction phi is made in this simple view of two components, phi mu, which really is friction, and psi, which is this geometrical effect of the difference between the microplanes of sliding and the apparent macro plane. So there are two components, friction and dilation. A question of a semi-technical nature. Can I plug a mouse into this computer? Does anybody think? Because I have a mouse. I've forgotten how much I use. My pointer. Very good. Thank you very much. Sorry about the interruption. Thank you. Oh, yes, yes. So, having introduced that, that there are two components at issue in what we call the angle of friction of soil. I now spoil that by pointing out that if you do discrete element analysis, as Colin Thornton did with his research student Barnes in 1986, and if you plot the magnitude of contact force between two disks, this is two-dimensional array of disks, where the thickness of the line, to your eyes, the blackness of the image on the screen, is proportional to force. Then when you isotropically consolidate the disks, the stress does not transmit from the boundaries in a democratic fashion. It collects in, as you see, in groups. So here, more or less like circular group, a circular arch thrust traveling round there, and another one here, and an assembly of them. So that is isotropic all-round pressure. And then if you apply deviatoric stress, these chains of strong forces travel mostly vertically. So deviatoric force aligns itself in groups of particles that happen to have collinear contact forces. So chains of grains that have almost coincident contact normals can act as potential struts in a three-dimensional, since soil is actually three-dimensional, a three-dimensional truss, which is a granular structure. The other grains that are carrying almost no force act as sufficient bracing to the truss to prevent it buckling or disintegrating. Eventually, if you increase deviatoric force, there is deformation at grain contacts, maybe crushing, maybe sliding, that causes links to disintegrate. And then the grains have to find a new equilibrium. So the grains move until, almost coincidentally, some arrangement of grains finds it can carry the load. So that is the source of deviatoric or shear strain. It's the grains slightly readjusting their position in order to find a new stable, strong force network. At peak strength, when the assembly can carry no more additional deviatoric force, then there is continued deformation that registers as plastic deformation. Even, well, so let us move on. And now some further information. The angle of friction of silicates on silicates. So an atomic plane of quartz sitting on another atomic plane of quartz, like two glass-like surfaces, has a very low friction angle of about 10 degrees. So there's a paper by Matthew Coop and his co-workers, Senetakis and Todisco, in 2013, demonstrating this surprisingly small friction angle. If you shear soil, sand, at constant density, and it's not dilating, maybe it was just loose sand, then you get a much larger angle, the critical state angle of friction. And you can get that from the ultimate strength in a shear box test or a simple shear apparatus, or a triaxial test if you go to the trouble of drawing a Mohr circle of stress and drop a tangent onto it from the origin. And then what you find is that for rounded quartz sand, you get maybe 32 degrees. If it's broadly graded, large particles interlocked by small particles, you get a larger angle. If in addition the shapes of the grains are angular, you get an even larger angle. So the question arises, if the angle of friction of quartz on quartz, for example, is 10 degrees, and the lowest conceivable angle that we call friction at a critical state, when you're shearing sand at constant density with no dilation in this case, is 33 degrees, where does the other 23 degrees come from? And to cut a long story short, it's sort of difficult to illustrate why that is the case. We just find that it is. We find it in soil tests that 33 degrees opposes 10 degrees. We find it in discrete element analysis, where the computer analysis of the contact deformation gives us, if it's a very careful simulation, the same large angle that we would call the critical state angle of friction. So it is to do with the statistics and the temporal nature of contacts continually varying from one force chain, which becomes unstable and goes to another force chain. So every increment of shear, there is a different arrangement of forces responding to the loads. And unlike the initial picture I showed you of two grains interfering, this is much more complicated. So all I can tell you is that this more complicated picture of internal statistical variation gives you a critical state angle. And I'd be very pleased to hear whether anybody has an analog of critical state behavior that shows where the extra friction comes from in a simpler way than a discrete element simulation. What we find is, instead of the overall angle of shearing resistance phi being phi mu plus psi, in the case of dilatancy, we find it is phi crit plus psi. So we're now getting really large angles. Angle of dilatancy could well be 20, 25 degrees for a dense arrangement of grains. And phi critical, as you saw, is in excess of 30 degrees. So we're ending up with what we call an angle of friction, but only 10 degrees of the 50 or more degrees of the granular material can actually be called friction. The rest is a geometrical addition due to the way that grains under force move against each other. Okay. As stress increases, the dilatancy reduces, but the critical state angle of friction remains the same. So by experiment, or if you like, by calculation in a discrete element simulation, one way or the other, you discover that the critical state angle is more or less constant. So in the end, the arrangement of strong forces that I showed you, that exists in a granular material at any state of dilatancy. So even at a critical state, there is this non-democratic distribution of internal contact forces. And so we finally arrived at the well-known position that if we plot secant phi, so that is dropping a tangent from the origin of a stress graph onto the Morse circle, or finding the inverse tangent of the stress ratio, shear stress over direct stress, then for a dense material, we get phi max, which, as I just told you, can be in excess of 50 degrees. And then that phi value drops eventually on continued shearing to its critical state value. If you've got loose soil, it painfully climbs up its shear stress strain graph until it reaches the same critical state value. The loose soil contracts, gets smaller in volume, the dense soil dilates. So this is familiar to us all, I suppose. And 40 years ago, I did a desk study looking at all the publications I could find that included the angle of friction, angle of shearing of sand. And I collected all that data together and was fortunate enough to see a pattern in it. So I picked what I considered to be papers by the top laboratories around the world, published in the top 6 journals. And there were data of 17 sands. And I'm not going to bore you with too much of that data, but I'm going to show you just a little bit of it. What I did was study the influence of relative density, defined in the usual geotechnical way, and grain crushing. And it's the grain crushing that creates the non-linearity in what I suppose we still call the more Coulomb strength envelope. Okay, and please pardon me in the English phrase, blowing my own trumpet on the last line. It now has over 3,700 citations, and there isn't a single piece of my own experimental work in the paper. It's all the work of others. All I did was, as it were, connect the dots. So relative density, where we are on a linear scale between the maximum voids ratio of soil at its loosest and the minimum void ratio of soil at its densest. I intuitively felt that that was a better measure of density than the absolute density of a soil in kilograms per cubic meter. Because that's actually very hard to define in the middle of a soil mass. It's very hard to find the voids ratio of soil. If you walk up to a dam and in order to analyze it, you had to know or find the voids ratio of the material 20 meters below the crest. You'd find that a very difficult assignment. Whereas if what you need to know is the relative density on that relative density scale of the soil, not today, but as it was compacted, then there should be site records of compaction that would indicate within a certain margin of error what the relative density would be. Okay. So that first definition of relative density was important to me. The second, of relative crushability, I derived by looking especially at triaxial tests conducted at high stress levels. Research workers spoke about hearing the sand crushing and discovering that the grain size distribution after a test was moved towards the finer side of grains when you sieved the sample again at the end of the test. And I made a definition that I'll show you in a second of the aggregate crushing stress. And typical values of that turned out to be 80 megapascals for sand, for silt, quartz silt, rock flour, 20 megapascals for sand, unless it was a carbonate sand, broken shell fragments, for example, in which case it would drop below that to some quite low value, like 5 megapascals. So if sigma dashed is the effective stress normal to a shear plane, so the confining stress in a shear box test, for example, or if in a triaxial test, you change the symbol to P for the mean effective stress, and look at PC dashed, those are going to be the crushing, aggregate crushing stress. And let me just show this. So you set up in the laboratory at very low stress level, when the logarithm of the mean effective stress is 0 and you're at 1 kilopascal confining pressure, arbitrarily down there, then you've got Emax and Emin. So in laboratory characterization or site characterization at low stress levels, that's a convenient measure to make. You can do that. But at very high stress, we know that all granular materials find what engineers call the normal compression line. So this is a much steeper line on voids ratio log stress. And in research this last 20 years or so, people working on micromechanics have understood that the normal compression line is a line of continual crushing of grains whose sizes fall on a fractal distribution, whose slope is about 2.6. It's another sort of mystery of life, a little bit like the extra 23 degrees. But in this case, entirely to do with the repacking of a granular material when the grains fracture and the statistics of that. Glenn McDowell, who was a research student of mine more than 20 years ago, who is now a professor at Nottingham University, has worked on that fractal aspect throughout his career. So we start off with almost indestructible grains as we increase the stress, and very small gradients on this compression plot, and we end up with normal compression. So I've marked off a place now which corresponds to the aggregate crushing strength as I imagined it, at about 20 megapascals, when the compression curve for dense sand and loose sand converge perhaps onto a unique normal compression line of continual particle breakage. Now, if you measure the voids ratio of soil continually shearing at constant volume, then by definition, that is soil at a critical state. And the critical state plot on this diagram of voids ratio against the logarithm of stress is also a curve until you get to high stress for sand. I know many of you are studying the behavior of clays in different experiments. You'll have to keep reminding yourself, I think, that everything is going to turn out to be the same in clays, but for MPa, you can refer to KPa. Clay agglomerates are at least 1,000 times weaker in breakage than sand grains. I've gone off at one of my tangents. So the critical state line is the red line. And so it reminds us that dense sand dilates if you shear it. So if you reach some stress level and then do a constant stress test, so that could be a shear box test, it could be a constant mean stress test in a triaxial apparatus, you would get an expansion of the material, and it eventually would reach a critical state. So even loose sand dilates at low stress. There is just a little bit of a gap between the critical state line above and the maximum void ratio below. It's usually impossible to set up sand in the laboratory so that it collapses on shear. Very difficult anyway. And even dense sand contracts under shear at very high stresses. So bearing in mind the importance of the angle of dilation to what we call the friction angle of soil, it seems important to have rules to predict how much dilation under these various circumstances you're likely to get. And so obviously you need two measures of relative performance. You need relative density that on the void ratio axis tells you where you're starting. And you need relative stress that dictates where you are between 1 kilopascal and maybe 20 megapascals. The higher the stress level, the greater the tendency to contract under shear rather than dilate. So if the dilatancy is a function of these two independent variables, it very fortunately occurred to me that a relative dilatancy index could perhaps best be defined by multiplying the relative density by the relative crushability. You recall that the relative crushability was the natural logarithm of the aggregate crushing stress divided by the current effective stress level. So IR equals IDIC minus 1 is an empirical equation that I saw coming out at me when I looked at all these different publications on the strength of sand. And what it told me was that phi max minus phi crit is roughly, well, actually quite accurately, 0.8 times the angle of dilatancy. At the start of this talk, you'll remember that I got something analogous. I got phi max minus phi mu equals psi max. Well, that wasn't right. And so an analysis of real soil behavior has taught us that we needed the critical state angle, considering statistical and temporal variations of contact forces. And instead of being unity multiplied by angle of dilation, it's apparently best to say it's 0.8. And equally, that is 5 degrees multiplied by the relative dilatancy. If you're in a triaxial apparatus, because you're wasting dilatancy over 2 dimensions in a triaxial sample, you don't get the full benefit of 5 degrees times the relative dilatancy. You only get 3 degrees. In all conditions, what Rho in his stress dilatancy equations plotted was the rate of change of volumetric expansion with major compressive strain. He liked that measure of dilatancy, and that's 0.3 times the relative dilatancy. So at the aggregate crushing strength, grains are breaking, volume reduces strongly in normal compression. But any moderate stress level, significantly below 20 megapascals for sand, the grains will not split, but the shearing will knock asperities, knock the corners off grains, making dust, and slightly reducing dilatancy. So the effect of that was shown, for example, by the data of Berlin sand, quoted in that 1986 paper. And so here's the full variation of angle of shearing. So phi max minus phi critical in degrees, somewhere on the range 0 to 17 degrees for Berlin sand. At 20 kilopascal stress level, yes, maybe 17 degrees at 95% relative density. But if you raise the stress level to 600 kilopascals, I think this was De Beers' work, you've dropped to 7 degrees. And so you've reduced the secant angle of friction by 10 degrees. And at every different stress level, there's a different black line here representing precisely the correlations that I showed in the previous slide. You know, the 3 degrees times relative dilatancy, or 5 degrees, depending which apparatus you're in. Here, it's the 3 degrees. The typical deviation between all these test data and what I've shown you, with IDIC minus 1 as relative dilatancy, and 3 degrees or 5 degrees as the extra angle, is only about 1 degree. That's the standard deviation. So here we are. Imagine that you've done a single soil strength test, maybe a shear box test. So you've got your first data point here of shear strength versus mean effective versus confining stress, effective confining stress. So that's the red dot. What will you then do? You will remind yourself that you want a range of stresses. So you will go on to do perhaps 1, 2, 3, 4 more shear box tests, and you'll get a range of data that would look a little bit like that. And then, unfortunately, what we've been taught to do since the 1930s is to take a straight line fitted to some part of this data and to give it the equation, strength is C dashed plus sigma dash tan phi dash. A most unfortunate circumstance, because what do you call phi in this case? You would call it people do call it the angle of friction. But Coulomb would not recognize that as the angle of friction. Coulomb would recognize the ratio of shear to normal stress. That was his ratio. And worse than that, we've ended up with an intercept, C dashed, that, as you can see in the data, does not exist. And so it needs a name. Engineers want to have straight lines. So C dashed is now brought into existence. And at least in the English language, it's called true cohesion. What is it called in French? It is called true cohesion. I mean, I feel as though I ought to be blaming Karl Terzaghi and that it all comes down to some original German misconception. I don't know. It's a silly name, isn't it? Because dry sand has no cohesion of any sort at all. And errors arise so that, again, obviously, at low stress level, below where the data falls below the tangent line, you've made an overestimate of strength. And at high stress, you've underestimated the strength, because anything beyond the critical state stress is now on a line of constant slope all the way from the origin, where that gradient is the critical state angle. And you've now underestimated it for no good reason. So what you could do instead is simply accept that the correlations I've shown you are a reliable guide to the strength and dilatancy of sand at every point. So if you use effectively the information I've given you, and you say phi max, the largest Moore circle, is phi crit plus 5. That's the 5 degrees in plane strain when you're not wasting any dilatancy. 5 degrees times relative density times relative crushability, which is the natural logarithm of the crushing stress divided by the current effective stress level, -1. That lets you plot each one of those data points fairly precisely within 1 degree deviation statistically. So it's a sort of polar representation of the data, not a Cartesian representation. But there's nothing wrong with it. Mathematically, it's well defined. If, on the other hand, you insist on drawing a curve through the data, then at least it will be a curve. And it turns out to be a power curve. That is, its equation is tau max over tau crit is sigma dashed over sigma crit to some power beta that's a simple function of relative density. So relative density 0, you just get the straight line to the origin. Higher relative density, it's got a little bit of nonlinearity to it. And then beyond the critical state value, linear. So you can approach it either way. You can take the expression offered, a phi against log stress, and use it that way. Or you can fit a power curve by plotting the logarithm of stress on the axes. And all you've got to do to predict the strength of sand is to recognize that phi max is a function of stress, as I've just shown you. And of course, in a problem that you've got, a dam or whatever situation you might want to analyze, the stress is a function of phi. So you have to make an iteration by guessing a phi value and then successively correcting it as you keep reanalyzing the problem to find what a better estimate of what the stresses are. And therefore, now you've got a better estimate of the stress, you can get a better estimate of the angle of friction. Well, our personal computers are so fast these days that there's no reason why we shouldn't all be doing that. It would endlessly remind us that phi, the angle of shearing, is not a material constant, as I've just spent quite a long time illustrating. So yes, you would need to do an iteration. Ueno, Japanese research worker, and his co-authors did a finite element analysis in 1998. So that's nearly 30 years ago, in which that was exactly how they got their solutions, doing another layer of iteration in a finite element analysis, which already is a little bit iterative. And then just the final note at the bottom of this slide is just to remind us that sometimes you don't want the peak strength. If you're in the middle of an earthquake, then the soil has been shaking and shearing cycle by cycle. And if the mobilized angle of shearing is greater than the critical state angle, but of course, to be stable, smaller than the strength phi max. If that has been happening every cycle of an earthquake, then each cycle there's some dilation. The soil gets looser and looser because of the dilation, and it ends up at having a strength of phi critical. And the same if you've got a landform subject to groundwater levels, and the groundwater level varies season by season, that might have exactly the same effect as an earthquake in continually shearing the soil, causing episodes of dilation. So that was sands, and it's 3 o'clock. So if I were to show you the details of too many other sorts of material, we'd still be here when it's time to go home. So I'm going to accelerate now through some other aspects. Clays. This is a hypothesis, as the title of the slide suggests. Clays consist of platelets. Pierre Delage picture of clay is sort of typical. It seems as though there are platelets, units of clay, stuck together by forces into books or chains of particles, trapping relatively large voids. Why not treat that arrangement of platelets as crushable grains themselves? So you're not trying to imagine the crushing of a single clay platelet, but of a group of them. And we know that what's important with clays is that as you consolidate them, you will squash the voids down. And then if you let them recover back to an over-consolidation ratio, the soil will seem to be quasi-elastic, but it's possible to destabilize the clay by shearing it, and then there will be further collapse. So in the data, for example, of Pierre Vichet and his research student Hattab, 2004, we can see a normal compression line that I would now call fractal compression, a critical state line parallel to it, or maybe it veers off to the left a little bit, curved here. And if you over-consolidate, in this case from 1,000 kilopascals, this is kaolin, and you stop off separately at these individual stations and do constant stress tests at different over-consolidation ratios, then, as I showed you for the sand, you've got contraction at high stress. It's just that high stress here is anything bigger than about 250 kilopascals, and low stress is anything smaller. And so there's the dilation at low stress. So clay and sand share the same features when you consolidate and shear. And as John Atkinson of City University in the UK showed at about the same time, 2007, if you plot deviatoric stress, mean effective stress, then again for over-consolidated kaolin, you get what should now look like a familiar curve of data, which if you plot on logarithmic stress axes, plots as a straight line. So this is another power curve, not a linear Moore Coulomb strength envelope. And then if you continue shearing, you get a critical state angle, which for clays tends to be about 23 degrees or thereabouts. So that was clays. Rock joints. So this is a cartoon from Nick Barton's paper in Rock Mechanics and Geotechnical Engineering, where this is actually based on real data, and intact rock is this nonlinear envelope of T against S dashed in this case. So shear stress against a slightly different definition of mean stress. Fractured rock going through the origin. You can pick a fractured rock off with your fingers. And so again, cohesion seems to be the wrong word to describe what it has. Jointed rock, a lower curve, but again, a curve of strength going through the origin, and filled discontinuities. That's where you've got clay, perhaps washed into the discontinuities in a rock mass. And so this is more like the angle of friction of clay. And in rock mechanics, the derivations of strength, that was started by Patton in 1966, writing an equation that is identical to the equation I started off with, the interlocked particles, like interlocked saw blades. Bolton and Chubet modified it to the second set of equations I had, where he called this a residual angle of friction. It's what I think we would now call critical state angle. And the extra dilation was a roughness coefficient multiplied by the logarithm of the uniaxial compressive strength of the waviness or asperities in a rock joint compared with the mean normal effective stress. So it's identical to sand and clay, but with different definitions. Bolton was very careful to define those terms so that they could be related to field tests on rock joints. So rewriting in soil mechanics terminology, Tormax is sigma dash normal tan phi crit plus psi. That's effectively the same for sand and clay. And the dilatancy is defined as a relative roughness multiplied by this logarithmic ratio of crushing strength to current effective normal stress. And what was important to Nick was to find a practical measure of these two parameters that he's introduced. And he specifies a Schmidt-Hammer rebound test, which correlates very well, so he assures us, with the crushing strength of the asperities in an uneven rock joint. And you do tilt tests or shear box tests to find the parameter R that fits the data. So all these different materials obey the same sort of laws, and the only difference between them is one of convenience of definition. In clays, it's easy to consolidate them, and so we tend to reference the consolidation stress instead of a crushing stress. In rock joints, it's the exact opposite case, and you may need to do a rebounding hammer test to empirically estimate the compressive strength of asperities. And in sands, well, you're sort of in between the two states, but you do need a definition of relative crushability and relative strength. Now, I'm eating up your afternoons here, unless I'm very careful, but I have a demonstration, a calculation and a centrifuge experiment that I'd just like to show you if you've got the time. If you've got other engagements, I will entirely understand if you file out to go and do some real work at some point. But otherwise, I'm going to keep talking for maybe 10 minutes. Okay. If you want to predict sand behavior, I'm talking about the vertical bearing capacity of sand. I'm imagining the seabed and putting a foundation pad down and applying force to it. No shear, just vertical force. The way we all handle this, I think, is that we estimate the relative density of such a sandbed empirically through the existence of correlations between the difficulty there is forcing a penetrometer into sand of different relative densities and its relative density. So there are various calibration chambers around the world that people have used and published various correlations. So we move from CPTs, cone penetration tests, to relative density empirically. As I remarked much earlier on, the actual density of a sand bed is quite hard to determine. But we can grab disturbed samples of sand and find its critical state angle. We don't need an undisturbed sample for that. And we can deduce the crushing strength by doing a few triaxial tests at any known relative density and use that empirical expression I showed you to find the best value of the remaining parameter, which you don't yet know, which is PC, the crushing strength. So you might like to see 2 or 3 independent estimates of that. If you are serious about knowing the answer, you might want to take account of the shape of the foundation, and there are empirical expressions for that based on people having done model tests. What everybody uses are Terzaghi's bearing capacity factors, and I'll show you how they relate in just a second. One question that everybody has is whether in these circumstances there ought to be a grain size effect. And this is something that's very conveniently discovered in centrifuge model tests, as I'll show you. So I had a research student, C.K. Lau, working with me. And about 10 years after he'd finished, we eventually managed to get our work published in Geotechnique. This was mainly, the long delay was mainly our fault in not immediately responding to the referees when they criticized our first attempt to get it published. So we wrote a theoretical paper and we wrote the final data up in an experimental paper. We studied Châtelet flint grit, very angular silica sand, And CK was an outstanding research student, very patient. And he washed silica flour, identical chemical composition, pure silica, but 50 times smaller. And he made sure that the grain size curve was identical, but 50 times smaller. So we could look at various scaling issues. It's a really nice thing to do for centrifuge modelers, and I recommend it. But you need very, very patient research worker to achieve this. And he did his own suite of triaxial tests on these two materials. And this is phi plotted against compressive strain from triaxial tests at all these different stress levels for sand on the left, silt on the right. And you'll see that I put a 50-degree line there, that the silt is consistently 4 or 5 degrees stronger than the sand at every stress level. And this should not surprise us because of the importance of crushing. So that is the fracture of grains. Small grains have small flaws, small micro cracks, and so they're stronger than big grains. And so at every level, there's more strength and therefore more dilatancy. And just as a note, I was always under the impression before doing this work that silt was inherently weaker than sand. Well, under some circumstances, it's not as reliable, for example, in liquefaction problems, but actually it's stronger. So there we are, plotting phi max minus phi crit against log stress, the silt on top, the sand below, linear lines against the logarithm of stress. The green line here is the empirical equation that I gave you 20 minutes ago. Sand turns out to be sand. And so the reduction of phi with log stress is linear, and it's due to the crushing of the material. So you could either say that the grains of sand are 5 degrees weaker, or you could say 5 times weaker, or you could say that the angle of friction is 5 degrees smaller. Both of these statements are true, empirically. So the variable phi I've shown you was phi crit plus some angle delta, which could be 3 degrees in axial symmetry, triaxial test. And then if you differentiate that equation with respect to stress, you get d phi by dp dashed is minus delta over p dashed times the relative density. I've just differentiated this equation. So this is a curved envelope of strength of granular materials. And we explained how to move from that to a stress characteristic solution, like Prandtl's solution for bearing capacity, but here allowing secant phi to vary. And when we did that, and we repeated the solution technique, here is half, as it were, half of a circular base. And when you push down on it and create a bearing capacity failure, this is the lowest stress characteristic, shaped like this because phi is varying. Look at the variation. Under the middle of the foundation, the stress level, in this case, this is a 5-meter radius concrete pad sitting on the seabed. The stress level is so high that you only just reach critical state angle at the bottom, 37.5 degrees. But as you move out into the solution, phi increases through 45 degrees, 50 degrees, 55 degrees. And when you account for that, you get an entirely different mechanism of failure and a different strength. So all that, if you're interested in chasing it up, is in the papers with Lau that appear on my website that you can download if you're interested. So we then did 1G footing tests with surcharge and found that these new stress characteristic solutions needed no correction for whether the sand was wet, saturated or dry, for whether we had a small foundation. So we were testing either 14-millimeter diameter foundation or 100-millimeter diameter, and whether the surcharge around the footing was 5 kilopascals or 200 kilopascals. So one analytical method solved every situation. There was negligible softening after the peak, no strain softening, and in each case, a good analysis. We had to take account of the change of geometry once there was settlement. This is Meyerhoff's effect, where this is very exaggerated. If you push a foundation down, you disturb the geometry of the failure cone, in this case, in this fashion. And this is explained, if this was a 1951 paper, 70 odd years ago, from Meyerhoff. So accounting for those two effects of geometry change due to penetration, permitting a greater angle in the failure surface, and yeah, we also did centrifuge tests, only 3, but we got very good results for this as well. So he tested sand and silt, 14 millimeters, 100 millimeters, different G levels. And once again, we got good back analyses of capacity with this new technique of permitting phi to vary with stress. And according to Meyerhoff, settlement to diameter ratios increasing. There was no chamber effect apparent with an 8.5 ratio between the chamber diameter and the largest footing. And there was no grain size effect at all apparent, even up to a footing to grain size ratio of 8,300. So this technique of solving the correct equations means that you're excused concern about other effects that you would have otherwise worried about. So when plotting data of foundation stress against settlement to diameter ratio of the footing. This is the N, gives you the N gamma value. So that's just using the self-weight term from Terzaghi, but you have to add the effect of the change of geometry due to Meyerhof. So all that was understood. In design, you'd simply use the N gamma value based on this intercept before you started worrying about the settlement geometry effect. And here on a plot of the logarithm to base 10 of the bearing capacity factor N gamma, 3.2 coming down to 2.1, and plotting against stress measured as the multiplier outside the N gamma, the 0.5 times the diameter times the effective weight of the soil in kilopascals, that the red line is a line of reasonable fit to the data, which are the red squares, and the green line is for the sand, and that's a reasonable fit to the empirical expression for sands. So the analysis, the variable phi analysis, fitted within half a degree of phi to the actual data. And these four green arrows are the end, almost like the end point of the lecture. In conventional practice, you might not recognize the difference between a 1 meter diameter footing with a stress level here of 5 kilopascals and a 10 meter diameter, 5 meter diameter footing with a stress level of 25 kilopascals. But what this picture reminds us is that what's at stake is a factor of maybe 5 or 10 between the different bearing capacity factors under these different circumstances. Silt being stronger than sand, red line above blue line, and the quite strong effect of stress level creating different levels of crushing in either of these two materials. So this is for very dense sand or very dense silt. So an engineer using one of the old textbooks like Terzaghi and Peck would very likely make an error greater than a factor of 3 in fitting a tangent to data that it didn't quite fit. And the disparity between a more Coulomb linear fit and using the actual data could be worth a factor of 3. So, and it will be the same story in a boundary value problem for fractured rock or for clay. So I'm trying to convince you that it will be worthwhile modifying any solutions that you like to use with a more Coulomb linear envelope so that you do this iterative solution instead and get the right phi value for each density and stress level. So I've shown you that you shouldn't really be using linear more Coulomb envelopes of strength. that the bearing capacity theory only had to be enhanced a little bit to account for variable phi and variable geometry. And then, notwithstanding grain size and footing size variations, the same analytical model worked within a degree or so accuracy in every case, with no strain softening. The vertical bearing capacity problem is insensitive to softening beyond the peak because you keep cutting into new material as you push down. So there we are. That was what I wanted to show you. That first of all, it's a little bit complicated. Then, thankfully, there are empirical correlations that appear to work as far as anybody can tell for all sands. That there's a little bit of uncertainty, but not very much, over the crushing strength of granular materials. But it's very easy to determine what that parameter is. And it's worth doing these things because otherwise, in different problems, you might generate an error of a factor of 3. Well, thank you for hanging on for an hour and a half. Oh, that's terrible. And I suggested if you have any energy left, that you could consider the role of empiricism versus constitutive modeling, or maybe how will we move forward as a profession when engineers are so reluctant to change their ideas that they were taught at school? What are the implications for ground investigation, stress analysis, teaching, research, or anything else? So if you've got the energy and you wish to ask questions, please ask.